This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you some improvements for my 10-channel temperature logger circuit. So in my previous video I showed you this guy here. I designed this and put it together, and this is a NTC thermistor-based temperature logger, and how it works is that it uses these microcontrollers, all of its 10 ADC channels, and then by utilizing a voltage divider, which consists of a fixed value resistor and a NTC thermistor, it measures the output voltage of that voltage divider, and then it calculates the temperature. And then the temperature values are shown on an LCD like this. And the data can be also saved on a SD card, because this LCD board also has an SD card slot. And I implemented all of these with this unit already, but then I came up with some improvements. So I will show you those improvements in this video, and I will build one more module just to have, let's say, an upgraded module. So there are several improvements that I implemented. One is the display. You will see it very soon when I show the display, but I picked another way of showing the data on the display, and I think it's a bit more fancy looking and maybe a bit more readable. You can decide if it's better or not when you see the results. And then another is more closely related to the circuit itself. And as you can see here, we have all the connectors, and then next to each connector we have the fixed resistors for the voltage dividers. So how I built the voltage divider is that the voltage for the voltage divider is supplied by a high precision voltage reference, and it gives 3.3 volts. And then that voltage reference feeds all these 10 individual voltage dividers here. And then what we have is that the top resistor in the voltage divider is the thermistor itself, so one of these probes. And then the bottom one is on the circuit right here, so that is a fixed value resistor. And originally I picked a 10 kilo ohm resistor because my probes are also 10 kilo ohm. So it made sense that when we are at room temperature, then the output voltage should be half the supply voltage. So I feed 3.3 volts to the circuit. Then the output voltage will be 1.65 volts or something like that, because then this probe also has 10 kilo ohm resistance at 25 degrees. So at roughly room temperature. But then there is an issue. As you will see it when I talk about the code on this microcontroller, actually the linearity and the measurement range really depends on the value of these resistors. So in the next iteration, I picked 5 different values of resistors, starting at 10 kilo ohm and going up all the way to 220 kilo ohms. And with that, I can shift the linear measurement range of this device towards the more negative values. And that's what I want, because I want a bit more reliability and precision at the lower end of the temperature range of these probes. So by replacing the original 10K resistors to higher ones, we can have better values or measurements. And after assembling the circuit, I will do some experiments where I have some different low temperature sources, and we will see how the different things behave. And how I do it is that every 2 resistors will be in pairs, so the R1 and R2 will be the same fixed resistors, 10 kilo ohm, and then R3, R4 will be 22 kilo ohms, and then so on up until R9, R10, which will be 220 kilo ohms each. And then everything will be set up properly. So that is the other, let's say, big improvement. But I think what is more spectacular is with the display. So let me prepare everything, and then I will assemble one more circuit, and then after that we will see how it works, and we will do the measurements to see if we gain any kind of accuracy, or if we gain any more better results by changing the resistors. So here is the newly assembled circuit, and then here is the old circuit. You can see it's the same. And then I just prepared everything for the last few steps. But before putting on the lid and turning on everything, I want to show you that the thing works, because in the video where I showed that I assembled the voltage reference, you might have seen that I did quite an ugly job with the soldering, but I cleaned up the soldering and everything works just fine. So I just want to show you that we got the exact reference voltage that we want. So it cannot be closer to 3.3. So the circuit works, as you can see. And then all I need to do, I will have to put on the cap. But before proceeding with that, if you want to recreate the same circuit, I really want to recommend you PCBWay's services. So you can go to my website or check the link in the description, and then you can directly go to PCBWay's project site where I shared the design of this PCB. And then by using their services, you can get the same board, and you can build your own 10-channel thermometer. So check the link in the description. Head over to PCBWay.com and use their services for your projects. So now you can see I also iterated this front panel a little bit. So I centered the display a bit more as compared to the first version. And I also centered the button, and then I put a small text there. As you can see, 10-channel temperature logger. That was just for an experiment. The version which I will upload will probably not contain this text, because you can see that with the letter E, my 3D printer was struggling a little bit, so maybe the fonts are a little bit too small to be 3D printed. So I just have it in this kind of condition without any text, but with the perfect centering. And one more thing that I want to highlight here is that this display, more specifically this guy here, has two versions, and the version number is visible here. This is version 1.1, And you have to be very careful with this because the version 1.1, so the guy which I am holding in my hands right now, is slightly larger than the version 1.2, which are in these two devices. And that is very important because you can see the difference. If you have the version 1.1 of this display, you won't be able to use it with my 3D printed panel. So that's just some remark that you have to be careful with. But otherwise, yeah, it should be fine. So yeah, here we have the board with like a open enclosure. So I created or made all these connections by hand. You can see it's silicon wires, and then for here, this is for the display, and then on this side here, you can see these four are for the SD card. And then I have the 10 different thermistors, and I marked them. So I have some small numbers there. Hopefully it can focus, so I can see which is which. But I think the more fun part would be to turn the power on and show some action here. So I just zoom in. Now the display hopefully better visible, and then just power on the things. So this is version 2.0 now, because I made such a big change that I decided to make it version 2.0. So this is the new user interface. So we have bars here, as you can see, 10 different bars. And then on the sides, we have the temperature. And then of course, the menu is unchanged. So we have a start button, a stop button, and then Fahrenheit, Kelvin, and Celsius. And the text below says Celsius because that's the most recently set temperature unit. So this will stay as Celsius right now. And it says SD not OK because I don't have SD card. But later on when I show the code, I show you some stuff with the SD card. So then this will go SD OK. And below that there will be another blue box which will say the actual or recent log file name. And now we return to the main part here. So now you can see that these are at equal temperatures because obviously they are at the same temperature. There's nothing funny with this. But what I want to see is that I want to expose them to different temperatures, especially to lower temperatures, lower than 0, because the different thermistors are adjusted to be precise at different lower temperatures. So I want to show you how they behave at, let's say, below 0 temperatures. So let me grab some ice, some water in the cup, and then we will measure the temperature of that thingy. So here is my little test bench. So there is a cup of water here with some ice cubes in it. And this will be our control thermometer, which is just a thermocouple. And then now we are at room temperature. But now I will immerse all of these thermistors. So that should drop their temperature with about 20 degrees at least. And now you can see that their temperature already dropped, but they are already at the same temperature almost as the thermocouple. But we can expect, of course, more lower temperatures as the ice melts, because then the equilibrium should be around 0 degrees. I'm at nearly sea level, so this should be fine. But we can see that everything is roughly at the same temperature right now. So this is at 5.3 degrees, and then anything between 4.8 up to 6 point something. So far all the thermistors behave the same or very similarly. Now what I can see is that the ice won't make any difference. So I will set up another system, which can go below, let's say, minus 20 degrees, and we will see how we reach the different values at minus 20 degrees. So I assembled another test setup. I squeezed in every odd number of thermistors here. So 1, 3, 5, 7, and 9. So each of the R2 resistors are represented here. And then I have 4 other thermistors here in between the fins of this CPU cooler, like that. I just squeezed it in. So that will just measure some warmer temperature as the CPU cooler will get hotter. And then I skipped one, which should be, I think, channel 1 or channel 2. So the first group with the 10 kilo ohm R2 resistor. That will just measure the room temperature. And then as a control, I put a thermocouple also under the hood. Probably you can see it right there under the number 7. It's there. So that's that. And then there's a fan in between these 2 blocks of the CPU cooler here. And just before going mad on my arrangement, the air is being blown there, and towards that direction there's a lot of empty space to blow the hot air around the room. And also this is an enclosed volume, so the experiment won't be affected by this. And then I have a 12 volt power supply, so I just have to hook it up with the wires of the fan. Let's go. So this is kind of done. And then I can start the fan. Probably you can hear it. And now I should start the power supply for this Peltier cooler. And this Peltier cooler here is able to go down to roughly minus 25 degrees Celsius. We will see. So I set up the power supply. So now 5 amperes is running through the Peltier cooler. And you can see that the temperature is already dropping. Of course, the thermistors need more time because they are in a metal capsule, as you can see, or as you can see. And that obviously requires more time to, let's say, thermalize. So it will need some time to get the temperature from the cold side of the thermoelectric cooler. So yeah, let's wait a few minutes, let's say like 10 minutes, and let's see what will be the temperature all across the probes. So now at least 10 minutes passed, so let's check the temperatures. And in the meantime, first of all, I noticed that the dial here was in the wrong position, so of course I fixed it, but when I started the experiment, that 18 degrees was not degrees but some other units, because I left it in this other position, but now it's showing minus 21 degrees. And then just to be sure, I added another thermocouple somewhere towards the side. Probably you can see the green wire, and that is also showing, let's say, minus 19 degrees. So 2 degrees plus minus, that can come from the difference between the positions, because the white wire is at the very center of the Peltier cooler, where it is cooling probably much better than at the side where the green is located. So then probably that can cause the discrepancy in the readings. I will try to see. So now you can see that this is more centered and it went up in the temperature. So yeah, the difference is really just because of the position. But what is more interesting is on this display. So I try to zoom in if I manage, and show it, let's say, like this. So what we can see here is that almost all the NTCs are showing the same temperatures, and you can really distinguish those which are on the surface of the Peltier cooler, because they became blue. Because one other cool thing that I implemented, I want to show you when I show you the coding, is that I defined some arbitrary temperature ranges, and whenever those temperature ranges are active, so we are measuring within those values, then the color of the bar changes. And then now the temperature dropped below 0 degrees, so the bar became blue. And then the green bar is between, if I remember correctly, 0 to 35 degrees Celsius. And above that it should become like yellow, and then orange and red. But the peculiar thing here is that I could not really reach very cold temperatures, and probably that is due to the bad clamping, because you can see that some of these guys could go down to like minus 14 degrees, these two, and then something is wrong with this. So that is probably at the side and not clamped properly, or something like that. So the experiment pretty much failed. Because what I wanted to show you is that actually those thermometers which are towards the bottom of this, let's call it list, or bottom of the display, those are the ones which are with higher R2 resistor values, and actually they should perform better, so they should show better values. They should be more close to the thermocouple readings, but that's not the case. So that is probably because I could not clamp it properly, and then it would make quite some effort to do it one by one. So let's just leave it like that, and let's just trust the physics that actually if you change the voltage divider, then you can shift the measurement range, and I will show you that actually with some equations and stuff, so hopefully you will believe me. But then one thing I want to show is that I have another thermometer here which I can heat up, and I will use a heat gun just to heat it up, and then we can see how the rest of the scale look like. So I just put this somewhere, and then I bring the heat gun in, and in the meantime I turn off the power supply of the Peltier coolers. So this is thermistor number 1, so you should look at this guy here, or number 2 probably. Yes, it's number 2, so you should look at the second line. And you can see that now it became yellow. And now it became orange. And now it became red because it passed the 100 degrees. So let's leave it like that and let it cool down. So now we can see that as the thermistor cools down, then the color of the scale also changes, or the bar. So now it is orange, and now it is yellow because it dropped between 75 and 35 degrees. And I can speed up this process. So I'm just using a fan to cool this thing more quickly. But you can see that it has quite some, let's say, thermal inertia, so it takes some time to cool it down. But see, if we will drop below 35, it will become green, the bar. So yeah, now we are at room temperature pretty much. And now everything is just cooling or equalizing the temperature. And you can see that the surface of the Peltier cooler is already at roughly room temperature, or at least yeah, the thermocouple, this guy. So yeah, this was the experimental part. So I wanted to show you the new display, as you can see, and the new front panel, and also I wanted to show you the principles of changing the resistors in the voltage divider. But when I show you the code and I show you the equations, I will show you some charts. And also I want to encourage you to go to my website because I wrote an article about this. So you can see the equations there, the charts, and some more explanation that I probably maybe forgotten when I was recording this video and things like that. So check that. And now let's head over to my computer and let's see, basically what is written on this microcontroller. So this is the Arduino code, and I will go through it line by line. But if you don't want any explanation, but you still want to have the code, I encourage you to become my supporter on Patreon. I always upload the source code there. And if you are supporting me, then you can get the code available for download. Otherwise, you can just follow the video and then you can see how I explain everything, and you can write and copy the code as I progress with the explanation. And one more thing is that I will make this explanation a bit more concise in terms of speed and depth of explanation, because some parts I have already explained in the previous video, so please check the explanation there. And then I will focus more on those parts which are new in this code. So yeah. So I always have a lot of information as a comment, so read them and then follow the instructions there if there is any instruction there, or just take those advices if you want. So we start with the libraries. We have the Adafruit library to take care of the display, and then the SPI because we want to communicate with the display and the SD card slot. And to be able to work with the SD card, then I use the SDFET library. So then here I defined some pins. These are mainly the pins for the SPI connections, both for the display and the SD card. But then I also defined the button pin, which is used for navigating in the menu. And then we have the sensor related parameters here. So the supply voltage, which is supplied by the voltage reference. The V out is the calculated or measured output on the ADC. When I said calculated, it is calculated from the, let's say, digital value, because you have to convert the digital value, the bits, into voltage. So that's what I meant. And then the RNTC is the calculated resistance of the thermistor. And then we have a nominal value of the thermistor. These are needed in the formulas that are used to calculate the temperature later on. And then we have the beta coefficient for my sensor. It is 3950. And then I have the room temperature, or more precisely 25 degrees Celsius in Kelvin degrees. And then I store the final calculation in this temp_K value. So then that will be my parameter to be used in the calculations and in the functions. Then I have a bunch of variables here. These are the 10 ADC channels. I'm using all the ADC channels available on this microcontroller, and you can see they are marked like this. And then to be able to use them in a for loop, I put all these parameters or variables in a array. So then I can just use the array and put it in a for loop and iterate through the items, and then it makes all the calculations easier. And then I do the same with the temperatures. So these are the calculated temperature values, which are basically measured by the thermistors, and there are 10 of them. And then once these values are calculated, like you see it here, those are put in an array. So this is also for convenience. And then here comes one of the improvements or changes. So as I said, the linearity of the measurement depends on how we pick the R2 resistor in our voltage divider. And then I chose several different, let's say, magnitudes or values for the resistors. There are 5 groups. Group 1 is resistor 1, 2, and they are 10 kilo ohm, and the next group is 22 kilo ohm, and then 47 kilo ohm, 100 kilo ohm, and 220 kilo ohm as a resistance. So with this change, I can shift the value backwards towards the negative ranges. So the thermistors with larger R2 values, so towards the end of this list, should behave more linearly at the lower temperature regions. And then how this looks in reality, or how it looks according to the equations, I can show it to you right now by opening another window. So here you can see some curves and some table. So first of all, in the table, what you can see is that I collected some temperatures and the corresponding resistance of the thermistor from the data sheet of the thermistor, and then I plotted it. So that is on this chart. And then each point is basically one pair of data from this table. And then you can see that this curve is more or less exponential. So in the legend you can see this exponential equation, which I fitted over this set of points, and that is the dashed red line. And then now I have a relationship between the temperature, which is measured by the thermistor, and the resistance of the thermistor, and I can express this with an exponential equation. And that is really nice, because then I can go to the other curve, which is this guy here, and I can measure the output voltage of the voltage divider, or expected output voltage of the voltage divider, as a function of the temperature of the thermistor. And if we start with the rightmost curve, this guy, which is now highlighted, and it is with this very turquoise color, that is when the R2 in the voltage divider is selected as 10 kilo ohms. And if I keep increasing this resistance, I go towards the left. So if it's 22 kilo ohms, I have the curve shifted backwards towards the left, and then I keep increasing it, and then when the resistance of the R2 resistor is 220 kilo ohms, then I shift it back quite a lot. And how we should kind of understand this curve is that you can see that in the waist, or in the center, we have a relatively linear part, and that is basically where we want to use this thermistor, because then if we go towards the, let's say, higher voltages or higher temperatures, we can see that a very small change in the voltage can mean a lot of change in temperature, or the other way around, on both of the end and the beginning of this curve, or the head or tail of this curve. And that is not really ideal. And of course, we want to have like relatively precise measurements, so we try to use them in the center. And I put all the equations and all the calculations and more explanation on my website about these curves, so please also check my website, because then you can follow the equations as well. Now, coming back to the code, I have all these resistor values, and I will need to loop through them as well, so I just put them in a list again, or not list, but an array. And then here in the code, I just use the two SPI ports, SPI 2 and SPI 3, because the SPI 1 port is like kind of occupied, because I use the analog pins, and the analog pins and the SPI 1 port shares a few pins. So yeah, I cannot use them, but luckily this microcontroller has several SPI pins or ports, so I can use the SPI 2 and 3 buses. And then the SD card is located on the SD or SPI 3, so then I have to write this line, so then everything will be handled properly. And then a few variables for the SD card. So the SD will be the instance of the SDFET library. And then we have to know if we have an SD card or not in the slot. So that will be marked with this flag. And then how I save the files on the SD card is relatively simple, but it's quite, let's say, useful. So I always create a serial number for the file, and then that serial number is always increased. And then how the file is built up is in the next line, is this line. So log underscore, and then I put the file name number after this. So if I have a totally empty SD card, the file name starts at log underscore 0. And then the next time when we write the next file, it will be log underscore 1, and so on and so on. And I can treat this dynamically. So I will show how this works dynamically. So when we want to have like hundreds of files on the same SD card, how can we know where we left? That will be explained in a few minutes. And then there is another instance here for the file on the SD card. And then I just create this TFT object, which is just for the display. So we will always use this TFT object when we manipulate something with the display. And then some variables for the menu. Item counter, it just tells the code where we are standing in the menu. If we are over the start button, the stop button, and so on and so on. And then the next variable here keeps track of the selection. So we see if the menu item is just highlighted or selected as well. And then we can choose between 3 different temperatures. Fahrenheit, that is for my American viewers. I have quite a lot of viewers from the US, so why not make it useful for them as well. Kelvin, for more science-oriented people, and Celsius, rest of the people, including me, who use Celsius. So then I keep track of the selected or active unit of temperature by using this variable. And then we have some things to do with the button. So the button state is whether the button is pressed or not. And then since we just have a single button to handle everything, to move in the menu and also activate or deactivate stuff, I will distinguish between short and long press. So I have the variables for them. And then the rest of the variables, actually these 4 highlighted ones, are also related to the long press or short press. So these just take care of those, but I will explain them more when I go to the functions. And then the button time, I will use this to, let's say, debounce the button in a cheating way. So that's that. And then I have a few other variables. We have to know if the logging is running or not, so that is handled in this. And then this temperature update timer is basically the timer or period for reading the ADC. So this can be also called as sampling period or something like that. And then start time and elapsed time is using the millis, and they just keep track of the elapsed time basically. So when we start logging on the SD card, we will see the 0, 1, 2, 3, 4, 5, and so on seconds. So each line will have a timestamp, but it will be just in seconds. And the new data flag is just used for the code to only write on the SD card if there is new data available. So we first let the ADC conversion or conversions, all 10, to finish, and then that means that all the array items are updated for the temperature, and that's when we can finally write on the SD card. And then we have the setup here. So serial.begin, that is for the USB communication. I use it because I wanted to debug the code here and there, so I keep it in. And then sometimes I notice that the microcontroller can get stuck. So with this line, we can wait to establish the connection with the computer, or alternatively, we can just wait for 3 seconds. At least for me it worked, so I just wait for 3 seconds. Then we just send some message to the computer. We start both the serials. And then here, just a little remark. By default, the ADC resolution is set to 10 bits. So if you don't write this line in the setup, you will get wrong readings, because by default, for some reason, 10 bits is the value, but actually the ADC on this microcontroller has 12 bits resolution, so use it like this. And then here I just blink the onboard blue LED, so I can see that the code progresses. And then I start initializing the SD card, if there is any, and then finally I get to the display. So I initialize the display, clean the display, and then here within the highlighted area I basically print the welcome display. And you can see everything how it works. So you can set the cursor based on the X and Y coordinates to somewhere, and that's where you start printing the text on your display. And then you can select the font color, the text size or font size, and you can also select the rotation of the display, so basically the alignment. And in my case, I'm using the landscape alignment, where the SD card pins, so the 4 pins, are on the left side of the display, and the LCD pins, those 8 pins, are on the right side. So that's how my display is rotated within my small enclosure or front panel. And then, yeah, rest is just some garbage text on the display. And I wait for 3 seconds, and then I erase the display again to prepare for the next page. And I just print the so-called column frames. You will see what they are, but they are the black frames around the bars which move when you change the temperature. And then I print the first page. So I fill in the bars with the corresponding lengths of colors and with the text of the temperatures and so on. And then finally we have a push button to handle everything. So we define it as a pull-up with a pull-up internal pull-up resistor. So it will be an input pin, and also it will use the internal pull-up of the microcontroller. So then we have our loop here. It has 4 functions, and I will explain each of these one by one. So first, I just explain this function, which is the convert to temperature. So this will take one analog channel reading, which will be just the voltage, and then it will also take the loop iteration. So since this convert to temperature is always placed in a for loop, I want to know in which iteration of the for loop we are standing at. Is it the 0th iteration, the 1st, the 10th, and so on, because that will be used to read the correct items from the arrays, or write the correct items into the arrays. So I need to know that. And here this will be my final value, which is returned by this function. And then this is just the basic conversion of the voltage, or into the voltage. So we read the bits. This is in bit units, and then I just use this multiplication using the volts, so the reference voltage divided by the number of steps, which is provided by the resolution, and that will give us the voltage measured by the ADC of the STM32 microcontroller. And then I left some text here, but I will remove this because this was for me to debug the whole thing. And here comes an important line, or important 2 lines. So you can arrange your voltage divider in 2 let's say configurations. One is that the R1, the top resistor, is the thermistor, and the bottom one, R2, is your fixed resistor. That's how I did it. So then, of course, in order to calculate the R1, you have to use a certain formula. But then you can flip this whole thing, and your fixed value resistor is R1 and the thermistor is R2. Then there is another formula to calculate the resistance of now R2, because that's your thermistor. And then I just implemented both ways, but my circuit board uses R1 as the thermistor, so that's why I'm using this formula. But this is very important, because in one way you will get increasing output voltage with increasing temperature, and with the other way you get decreasing output voltage with increasing temperature. And then this can, I don't know, determine the application, how you want to use the things and so on. So just pay attention to these details. And then as I said, we want to store the resistor values, so the fixed resistor values in an array, and this is becomes very useful, because here we use the actual resistor based on the step of the for loop, and then we read out that certain item from the array and use it in the equation to get the resistance of the thermistor. And then other garbage here is just deleted. And finally we get this parameter and some other values, and we just basically substitute all the parameters in this equation, and we can get the temperature in Kelvin. So this equation is written in a way that it returns the temperature in Kelvin. So now we have to decide whether we want to return the temperature to the user in Kelvin or not. So then we check what is the temperature ID, and then based on the response, so which case is true, we either convert it into Fahrenheit, so you see the conversion, or we leave it as it is, or we convert it into Celsius degrees. And once that's done, we just return the output temperature, which is the temperature of a given thermistor, and then it's done. So then the next function is the write to SD card. So we only write on the SD card if the logging is running and there is new data available. If that's the case, we open the file, which is defined by the SD file name parameter. So for example, if this equals log_0, then we open that file. And if that file exists, so this one, this variable is basically equals 1, then we enter the rest of this function. And then, as I wrote it here, the SD library cannot handle floats. So then we use this d2strf function, which converts the float into basically an array of characters. So then what I do here is that first I want to print the time on the or in the file. So that will be the first column. And first I create a buffer for it. And then what I do within the d2strf is that I have this floating point number, which is the elapsed time. I have 5 characters, so that is the same as the length of the time buffer. I want to have 1 decimal points, for example 10.1, and then I want to put the result of this conversion into the time buffer character array. So then the d2strf does it, and then I can finally print this buffer on the SD card. And after printing the number, I will print a comma and a space, so the file will look like as a CSV file. And then I will do the same within a for loop for all the 10 channels. So that's why the for loop goes until less than 10 from 0. Because now I have the data, so I just created a data buffer. I convert it following the same strategy that I just explained. So print all the values, so every ith value is printed, and the comma with a space is placed under the value. And after the last iteration, we print a line break, and I close the file. And yes, here you can see that even in the last iteration of the file, there will be a comma after the 10th value. But yeah, I was just lazy to skip it, but actually I can make this, let's say, perfect. So if, and I will explain what I have done here. So what I have done here is the following. So if I would have a file that would look something like this. With the original code, but now I changed it. So what happens here is if the I is not equal 9, so basically 0, 1, 2, 3, 4 up to 8, then we can print a comma. But when the I equals 9, so that's basically the last iteration within this for loop, then we don't print the comma. So we just directly print the line break. So I just did this right now, so now this will look a bit more professional. So then once the for loop is done, we actually fall into this line. So we make the new data false again, so a new AD conversion can start. The 10 channels can be converted into the array items, and then that will trigger a change in the new data again, which will make it false, which will make it true, and then that will allow us to write on the SD card again. So then we are at the init SD card function, so it's initializing the SD card. And then what happens here is that if we could not start the SD card, then we flip this variable and make it false. So SD card detected equals false. So then the display will know that it should print something to tell the user that the SD card was not detected. Otherwise, this will be true. Again, we can print something, so we let the user know that the SD card is detected. And then this line is for a very specific user also, who was curious about how to do this. So it's, if I'm very strict, this is 3 lines. I can do this, and I can do maybe this to make it 3 lines. But I mean, it's really a short code. But what happens here is that we already predefined how we want to format our file name. And that will look like this, log underscore and the serial number of the log file. So log underscore 0, for example. And this has to be always, this file name strategy has to be always consistent. So what happens here is the following. This line looks at the SD card, the content of the SD card, and then it checks if the file name exists on the SD card. So first looks at it, is there any log underscore 0? Let's say yes. So then the function enters, and now the file name number, which was initially 0, becomes 1. And then we generate a new file name, which will be log underscore 1. So then the function goes back to the SD card again and looks at the contents of the SD card. Is there any log underscore 1? And let's say yes, there is. So again, this gets increased to 2. So now we generate a new file name, which will be log underscore 2. So then, again, this line goes back to the SD card, looks at its contents, and checks. Is there any log underscore 2? And let's say no. So then we skip these because the line here said no. So then we cannot enter, so we just proceed. So now we know that our file name, the new file name, became log underscore 2. So for the sake of checking, I just print this on the serial port, and then I proceed using that new file name, the newly generated file name, and I write a header on it. So this will be the header, basically, that time, and then the 10 temperature channels, and then a line break after it, and then finally I just close the file, and then that's it. So then we dynamically generated a new file, and this works always, and I can even demonstrate this. So I will take an SD card which already has plenty of these log files, and then we will see if we can generate a new one dynamically. So let's do that. So here is my SD card. This is the SD card that I use with the temperature logger, and then you can see that it already has 7 files from log 0 to log 6. So now I'm going to insert this SD card in my temperature logger, and then we will see if if we can get the log_7. So let's see. So I'm about to connect the microcontroller to the USB port, and then you can see that I brought up the serial terminal. So I have connected the SD card in the slot of the display. So let's start up everything. So you could see basically this part going on. So what we have here is that we see the list of the files, and then at the end we have the final file name created on the SD card. And what we really want to see here is whether it is really existing on the SD card. So now I will just start the logging, so that will write some data on the log_7 data file. So I now stop logging, and there will be also log_8. So now I disconnect the USB, and then I connect my SD card to my computer. And there we go. We have the log7, and I can open this. So there you go. I haven't uploaded the new software, so of course we have the comma here, and this is what I fixed when I explained the code. But otherwise you can see that we had some logging. And now I just have some garbage data here because I'm using a board assembled on a breadboard, and I don't have all the NTCs connected. You can see it in this column that I have an NTC here, and actually I'm using a resistor here, or potentiometer, but the rest of the columns are garbage. And then if I open the log_8, then you can see that that's just with the header. So you can see that the dynamic file naming works pretty well. So coming back to the code, we are finished with this part. So we initialize the SD card, and then we basically just printed the header, and then the function is completed. So now the next part is the print second page function. So that is where we have the stop button, the start button, the Fahrenheit, Kelvin, Celsius buttons, and some information. So we will use larger font here. So I set the text size to 3, and then I erase the screen. And then here I don't really explain everything one by one, but this is like creating the background box for the start button, put the cursor inside the start button. So now it's an empty blue rectangle, and then I set the text color to white, and then I print the text over the blue rectangle, which is start. So this will be my start button. And then I just do the same with the stop button. So just different coordinates, but the same thing. And then also with the Fahrenheit button, the Kelvin button, and the Celsius button. So these are all the same, let's say, ideas. You just put the box somewhere else, and you print the text somewhere else. And then we have some other boxes with some smaller text. So I bring down the text size from 3 to 1. And then again, I just create a box, set the cursor inside the box, and then select the text color as white. And then based on the active temperature, which we selected, I print the text in it. So then this will be that small text that I showed that shows the currently active temperature unit. And then we also have some boxes here which just decides what to print based on the detection of the SD card. If we detected an SD card, we of course write SD OK, otherwise we say SD not OK. And then, if there was an SD card, we also want to know the file name of the actual logging. So maybe for later use, this can be useful for the user. So then, again, just print a box somewhere, and then at the end we print the file name inside that box. So the user will see that, oh, now I'm logging log_9. And then at the end, if you have noticed, there is a small red or green rectangle at the bottom right corner of the display. And that is just as an indication whether the logging is running or not. And then, yeah, I just fill it accordingly. Green is logging is on, and red is logging is off. And then the function is done. And here comes a bit more sophisticated part of the function or functions. So this is the update selection. So first, this update selection activated has to be true. So that is triggered by a button press or something like that. And based on where we are staying in the menu, so that is determined by the value of the item counter, we do different things within these different cases. So the case 0 is when we are on the main page. And then when we arrive, this is basically when we arrive on the main page from another page, which was the previous. We erase the screen, and then I just print the column frames, and then I print the first page. And both of these functions will be explained in a few minutes. And then if I arrive on the second page, then I print the second page. And since we are always navigating forward, so we never navigate backwards, at this point I only have to print the second page once. And then I just highlight the start button, because when I arrive on the second page, the first item on the second page is the start button, so I can already highlight it. So then if the user will do a long press on that highlighted button, it will be already starting the logging. And then the case 2 is the stop button, and since we are already on the second page, we don't need to print the second page again. We just remove the highlighting from the start button, and how we do it is that we just redraw it with blue background, and then we highlight the stop button with red background, and that's quite simple. So yeah, it's just basically the same. And then we do the same with the rest of the buttons or items on this page. So if we move to the next, which is the Fahrenheit button, then of course we have to redraw the previous button, which was the stop button. So make it not highlighted, and then we highlight the Fahrenheit. And then here in the Kelvin page, we remove the highlighting from the previous item, which was the Fahrenheit, and then we highlight the Kelvin. And then same with Celsius, remove the highlighting from Kelvin and highlight the Celsius. And then once this is done, we make this false, so the loop, because this function is located in the loop, will not return to this function until the user presses a button again or moves inside the menu. And then the next function is checking the button. So as I said, there is a short press and long press. So this is always running. So every time when the loop is iterating, then this function will be performed. So we are polling the button. The rest of the things are not, let's say, computationally demanding, so I can kind of afford to poll the button. But if you really want, you can do interrupts. It's up to your personal taste. And if you have any time critical stuff. But here we don't have time critical stuff, so we can afford this tiny, I don't know, detour. So we read the button whenever we enter the function, and then we see if at least 100 milliseconds elapsed since the last reading. And this is kind of the debouncing, because if two peaks, let's say, come in less than 100 milliseconds, that typically comes from bouncing. So when you press or release the button, it is not just a simple, let's say, square wave edge, but it's more like several square waves after each other because of, you guessed it, bouncing. So then this is how I treat it with the code. But of course, you could do this with hardware as well. But the code is a bit less cumbersome in this scenario. So then we have to determine what happened with the button. So if the last state is high, so when we entered this function previously, and the current state now is low, then the button was pressed. So then we note down the actual state of the millis. Or if the previous state was low and the current state is high, so we release the button, then we again take a note of the current value of the millis. And then we calculate the elapsed time. So the time difference between the time when we looked at this part of the function and when we looked at this part of the whole function. And then we can decide if this press duration is shorter than the short press time, then of course we are just navigating in the menu. So as long as we are below 5, we just increase the item counter because we are navigating forwards. But then when upon the next press this item counter wants to be 5, we don't let it to be 5, but we make it 0. So we start navigating from 0 again. So we go back to the main page. And then we also let the other function, which I previously explained, know that the selection was active. So it has to do something with highlighting. So that function will take care of the display based on where we are, based on the item counter's value. And then if we pressed larger than the long press time, and as you can see in this pop-up, that is 1 second right now, then we do certain things. So if we accidentally pressed in the case 0, which is the main page, for longer than 1 second, nothing will happen because we don't want to do anything on the main page. If we did it over the start button, and if the logging is not running, then we start logging. So we make this true. We note down the millis, so we can have it as a reference time for counting the elapsed time. We make the item counter 0, so that will, let's say, jump back to the main screen directly from here. And then we also print the main screen and jump out from this whole mess here. And of course, if the logging is running is true, and we try to start again, we don't do anything. So that's why we have an empty else branch here. If we are over the stop button, of course, we stop the logging and we create a new file name because we will know that we can potentially start a new logging within the same run. So we prepare the file. So that's what's happening here. And then we also have to update the text box in the screen or on the screen with the new file name. So that's happening here. And we still take the new file and then we create that new file with the header. That's what I showed you like 5 minutes ago, that after finishing the log file, we also created a new log file with the header already in it. We highlight the stop button, so the background becomes green instead of red, because what we say here is that it shows the user that we pressed it, and that makes more sense. So that happens here, and then we adjust the color of the small rectangle at the bottom right corner and make it red, so there is no logging running. And then here the next 3 cases will be the same. So if we long pressed over the Fahrenheit, then we highlight the Fahrenheit button with green, so the user will see that the long press was detected. We make the temperature ID to 1 because now Fahrenheit is our active temperature, and we print the text on the display as well, so we can also read it whenever we look at the screen, that we see that the unit is now Fahrenheit. And then the same with the Kelvin. Highlight the Kelvin, let the code know that now the active temperature unit is Kelvin, so that belongs to number 2, as you can see it in this pop-up window. And then finally we do the same with Celsius. So highlight, change the temperature ID, and print the actual text unit. And then the last state equals the current state, so that is just updating the most recent value of the button press, and then the button time also being reset. So then we can count from 0 up to 100 milliseconds again to avoid bouncing. And then we have this print column frames function. So this will be used every time when we use the first display or main page where we show the bars and the temperatures. So we first erase everything from the display by printing the whole display with white. And then we draw rectangles on the display. And this is basically the empty rectangle where the bars, the colored bars, move back and forth. And then these are just basically the size of that thing. So x equals 1, and then y parameter of the rectangle equals this according to the for loop. And then this is the width, and this is the height, and this is the color of the frame. And then also, since we cleared the whole display, we have to redraw the small log indicator. And then if it's green, then logging is on. If it's red, logging is off. And then we have to also print the rest of the page. And this part will be a bit more interesting. So if the item counter is 0, so that is when we are on the main page. And if there is more than 300 milliseconds passed, so now this is actually the update period or frequency period, to be very precise. So every 300 milliseconds we update the display, and that also means that we read the ADC. And what happens there is that here we have our for loop again to cycle through all the 10 channels. And then what happens first is that first we write the first temperature value as a text. So this will be the highlighted part right next to the first bar at the top. And then we have these 3 variables, because here I will do some tricks. So first of all, we have to take care of the different temperatures. And I will explain this only for one temperature, because it's the same for the rest of the temperatures. You just need to adjust a few values. So let's see the Fahrenheit. So I created this temperature, which is like temporary temperature value. And that is the reading of the ADC, and that is constrained between minus 67 to plus 257 Fahrenheit degrees. And why I have to do this constraint is because if I don't constrain it, I can read lower or higher values than this. And if I pass lower or higher values than the limits inside the next map function here, my bars will go crazy on the display. So I use this constraint. So if the temperature values would be minus 70, then whatever happens, the temperature value will be only minus 67. Or if the temperature values would become 300, then the temperature will become 257 only. And then we take this temperature value, cast it into long, because now it was float, as you can see up here. And then we just map our temperature between these two values. So what will happen is that we take the temperature value, which we read, and then we distribute it on this scale in a way that it will be represented on this scale. And what we have here is that this temperature range will be accommodated on this pixel range, because the 0 and the 121 is the bar length inside that black frame, which you could see on the display. And then I do a new reading, and I do the same, constrain the value between the previously already defined values. And then here I do a real reading, so I read the AD converter. And then here, I just printed this, which I don't need now. And then I calculate the box length again. And that will be, again, based on the new temperature value. And now I have an old box length, so that was the previous box length based on the previous temperature reading, and I have a new box length based on the most recent temperature reading, which I just did 2 lines above this line. So then I can move forward. So then there was a reason why we calculated the difference between the box lengths. So those are the square bars or rectangular bars, which represent the temperature. So then we want to see the previous temperature reading and the most recent temperature reading that we just did right here. And what we want to see is that if the previous was smaller than the other. If the previous was smaller than the new one, we don't care, we just skip this because the new one will be larger, we can like print over it. But then if we will print a shorter, let's say temperature bar than the previous temperature bar was, we will need to erase let's say the previous bar. And there is 2 ways. We can erase the whole bar and redraw the new one, or this is, I think, a bit smarter way. We can just take the difference. So let's say the previous bar was 120 long and the current bar is 100 long. So then we just erase the 120 and 100 part. And that's why we did these calculations and calculated the difference in the box lengths and so on. So we can just erase a small part by just printing white over it, a white color. And then that will make the code a bit faster. So you will see a more smoother display. And then after finishing with the boxes or erasing the boxes or just skipping the erasing, we just update the, let's say, numerical values. So there will be the number printed next to the bars. And then, of course, we have to draw the boxes according to the temperature units. So again, we check what was the ID, and now I just explain it for Fahrenheit. So if the temperature is lower than 32 Fahrenheit, then we fill in the box according to the length with blue color. And then if it's warmer, so if it's between, let's say, 33 and 95, then the color becomes green. So this is like human temperature, so room temperature and a bit higher temperatures. And then if it's even warmer, then it becomes yellow. Finally, it becomes orange. And if it's beyond this 212 Fahrenheit, then it becomes red. And then the same happens with Kelvin, but of course we have to take care of the units properly, because now we are restricted to use Kelvin degrees. And actually I can see one issue here and here, because I haven't updated those, so I will just update these. So this obviously becomes 308 and then 348 because of these previous parameters. And then now I also see that this should be 95 and this. So now it's correct. Yeah, now it looks fine. And then, yeah, so basically the same happens with Kelvin, and then it happens the same with Celsius. And the Celsius is correct because I wrote this function first, and then I just converted it for Kelvin and Fahrenheit. But yeah, it should be like this, and now it's correct. And then basically this is the end of the code. So then we exit the switch case, and then we restart the timer. So countdown to not 1 second, but 0.3 seconds, that starts over. And then since we did the conversion, then we let the code know that new data is available. So if the microcontroller wants, it can write data on the SD card. And yeah, basically that was it. So almost 800 lines of code, quickly explained, or at least as quick as I could. I think it will be rather long anyway. But once again, if you don't want to listen to this explanation and don't want to endure it, just support me on Patreon and you can get the code as it is. I will go through it one more time just to weed out all the issues if there is any, but I think now it should be very usable. So this was all regarding the updates for my 10-channel thermometer. If I will find any more issues or if I will find more stuff to improve, then I will make a new version and make a new video about it, but this will be, I think, quite okay for a while. Once again, don't forget to visit PCBWay's website, especially my project page, if you want to get this PCB. I shared all the necessary details for assembly and everything. And also check my website because I put some extra information and charts and everything there. So you will see it on my website. So I hope this video was useful to you. I hope you learned something and see you in the next video.